Hello, I am Imran. I am hardware engineer at Stelar. So at Stelar we have equipments to perform NMR experiments for field cycling and also for time division NMR. For field cycling we have two main instruments. One is Spin Master, which is our main instrument, which can be used from 10 kilohertz to 40 megahertz, and it has range in terms of Tesla, 1 Tesla. Then we have another instrument which is here with us. This is Smart Tracer, and it has an operating range from 10 kilohertz up to 10 megahertz, and this is a 0.25 Tesla benchtop instrument. Then we also have 3T, which is our time division NMR instrument, and that instrument has a range from 10 megahertz up to 120 megahertz. So that instrument with these instruments can cover the range from really low field, practically from 1 kilohertz up to 128 megahertz. Today for our training we are going to use this instrument, and I will explain to you its main characteristics, how you can switch on this instrument, how you can use this instrument, and what this instrument has capability. As you can see here, this instrument has two main parts. This is the main part where we have our NMR console and also console to control the temperature of the sample, and this is called variable VTC or variable temperature controller, and this controller can be operated manually by the user from here, and also this controller can be controlled by the software. Then this is our NMR console. So when the instrument is connected to the power supply, we just have to switch it on from here. The console is on. The next part is to make sure that the transmitter is on, which we can do from here. If you come here, I will explain to you what's inside this Smart Tracer. So this Smart Tracer has few important components. The most important of which is our electromagnet, which you can see it's here. And this electromagnet is inside this Gardner liquid, and the purpose of this Gardner liquid is to disperse the heat which will increase when we perform NMR experiments. And this heat through this pipe is exchanged using a heat exchanger enclosure, which is down there. I don't know if you can see it or not, but it's there. So with this heat exchanger, this heat is transferred from electromagnet to outside. And then we also have tuning box. The tuning box is one of the important parts of this device because it contains the circuitry to tune the probe, plus it also contains the circuitry to pre-amplify the RF pulses. So with all these instruments, with this simple instrument, with all these capabilities, you have an instrument which you can use in your labs, in your industries, to perform NMR experiments on your samples and to know their relaxation values. And before starting an experiment, this is really important that the sample must be correctly positioned inside this tube, and the volume should be like this range. So this is the standard range which we use to perform NMR experiments on our sample. And to correctly position it, you have a guidance line here. The sample has to be centered with this line, and then it has to be inserted here. So once the sample is prepared, it's inserted, then the next part is to go to our Storm 6 software, which is built to perform NMR experiments starting from mono-exponential up to multi-exponential experiments. So with this software, you can do all kind of experiments, and this software is really intuitive, easy and flexible to use. And now we will go there, and I will explain to you how you can use this instrument, this software, to perform your NMR experiments. So let's go to the screen. Storm 6 is a web-based software, and it offers you greater flexibility to access it. You can access the Storm 6 either locally or remotely. The remotely accessibility is one of the main features of Storm 6 software, which generally is not possible with other commercially available NMR software platforms. So in order to access the Storm 6 locally, what we have to do is to open any web browser, and this web browser can be of your choice. It can be Chrome or it can be Firefox or any other platform which you think is more familiar to you. You just have to open your preferred browser, and then you have to use address in the address bar. If the instrument is connected to the PC directly, then the best option is to connect to the console or to instrument locally. And to do this, we just have to write this address localhost with these extension, and then press enter. And this is how the instrument will connect locally to the software. And then what we have to do is to write the required username, password, and then press login. So in this way, the Storm 6 will log in, and this is the first page which the user will see. But let's say you, due to some reason, you do not want to perform experiments locally and you want to perform your experiments from your office. This is how I am. We will do this training sessions. Right now I am not near instrument, but I am at my office. So what I will do, I will access the instrument remotely. To do this, what I need is just the IP address of the PC which is connected to the instrument. And in my case, the IP address is this one. Then the second part is I have to use the same port number, which you see I used for local access. This 8000, I have to use the same here. And then I have to press login. And this will be the first page which I will see. And here again, I have to write the username and password to access the Storm 6. And on this, let me introduce you to another important advantage of Storm 6 software. This is multi-user capability. So Storm 6 provides different users to access, to manage their data separately from each other. And due to this multi-user accounts, this is really important whenever the instrument is used in a lab environment where many users use the same instrument, same device, and sometimes it's become really difficult to manage their data. And to overcome this, to allow users the possibility or the flexibility to manage their data easily, Storm 6 offers the possibility of multi-user login. So each user with their own username and password can log in, and once they logged in to the Storm 6 software, then they will only see those experiments which they have performed using those credentials. So in this way, the administrator of the device can create different user accounts for each users, and each of these users will be able to access the same software separately, and they can perform their experiments independent from each other and can easily manage them. Once the username has its ID, like in this case, this is my username, I will write my password. Then I just have to press login, and I will see this main page. And this main page is where we have workspaces. So workspaces is another feature which Storm 6 provides to its users. And workspaces in Storm 6 acts like digital notebooks. They are dedicated areas where user can group all experiments based on sample, based on project, based on user, just to separate and manage different projects, different experiments in a more efficient way. So as you can see here, after login, I am seeing some workspaces and they have different name. Like this workspace has name Stelar Test. This workspace has the name of Smart Tracer, and this is another workspace which has name of Training Workspaces. Just to let you know how this part works, I will create another workspace here. I will just name it Training NMR, and then here we can write any description of the workspace or the project on which we will work inside this workspaces. And to make things easy, I will write just a sentence here. write the description of the project. This part is not necessary. It's something if you want to add extra information about this workspace, you can write it. Otherwise, you just have to create and give it a name and then save and open. So as you can see here, this is a new workspace which we just created, and there are no experiments here. But to explain to you what is inside a workspace, I will go back. You just have to click here on Storm 6 account, and then I will open one of the already created workspaces. Okay, for our training purposes, I will open this workspace, and here you can see that there are some columns and some rows, and each of these columns and rows gives different information to the user related to the experiments they have performed, the sequences they have used to perform that experiment, and some other important relevant information. Okay, so let us go through the first column. So the first column has the label name. So what it means, this is the name of the experiment which user has given to that experiment when he created this experiment, and this name can be any name which user prefers. What we suggest normally is to give experiment a name based on the sample which you are using, the date on which you have created, just that in the future, let's say if you open the same experiment after some time, from this name you will easily identify why you created this experiment, why you performed this experiment, to give you some information which can be helpful in future. Then the second column is the date. Here it tells you when this experiment was created. So you see different experiments have different dates, and each of these dates tell you the date on which it was created, at the time, and also the day. And then you can manage them in ascending and descending manner. What it means that you can arrange them from oldest to newest, like this one is the oldest experiment, and the latest. You can manage them. Similarly, in the name side, you can arrange them alphabetically here based on the date. And then this tab is called sequence tab. So these are basically sequences which are available in Storm 6 software, which users can use to perform different kind of experiments. Because whenever you have to perform an experiment, the user should know what kind of experiment you want to perform, and based on that there are different sequences available in the Storm 6 sequence library, and he can use the sequence which he prefers. And since Storm 6 is a multi feature software, and this software can be used with our field cycling instruments and also with our fixed field instruments, and each of these systems have different kind of sequences based on the technology which they are using, and one kind of sequence cannot be used in other kind of sequence. To make things easy for the user, so that whenever he tries to perform an experiment and he selects the proper sequence which is related to that instrument, we have used these extensions. So if there is a sequence with name FFC, it means this sequence can only be used with a field cycling instrument like Smart Tracer or Spin Master. And if there is an experiment with FF extension, it means this is an sequence which can be used only with our 3T instrument. And then there are some sequences which do not have this extension. This is because these experiments are self-explanatory. Like if we have an experiment with CPMG, it means this is a fixed field sequence because this functions or works on single field value. Then similarly, if we have a sequence like NPS, PPS, these are field cycling sequences. So the sequences which are self-explanatory do not have these extension. But if there are sequences which need this extension, this is because the angle sequence is used for field cycling instruments and also for fixed field instruments, because this is the experiment which we use to get a proper pulse power, pulse duration, the flip angle, which in the second part of our training, I will explain to you how this experiment is used and what this experiment gives to us to perform experiment in a more reliable and efficient way. So this is a part inside a workspace where we have different experiments. And then the last run, this is another important column which tells the user when this experiment was last used. So here you can see this tells you about the date when it was created. Like this experiment was created on 10th of March. Similarly, this experiment was created on 7th of March. But the last time it was used on 10th of March, it means after creating this experiment, the user probably has used it all 3 days, or after few days he used it again to perform some different kind of experiments on the same sample by changing parameters or something else. So that's how even you created an experiment earlier, you can use it in your future in future whenever you need to do some changes or some modifications. Then the last part is actions, where by clicking on the view part, the user has the possibility to open the experiment which was created earlier, just like this, or the user has the possibility to move it to another workspace. Like as we can see, there are different workspaces, he can easily move it, and he can also delete it if he thinks the experiment which he created is not something which he want to keep, or the results which he has are not correct. So for any purpose he can easily delete the experiment just to manage or clean the workspace and keep only the experiments which are necessary. So once we are familiar with our software interface, how to log in it, how you can access it, how the workspaces are managed, how the workspaces can be created, then the next part which comes is to perform a real experiment. And in order to perform real experiment, the first thing which we have to make sure is the software is connected to the console. And to do this, there are some indications which the user can see and make sure if it's connected. The first part is that if the user is able to see the firmware version, which in our case now is F04, it means software is communicating with the NMR instrument and it can read which firmware is now in the console and which firmware it's running. And these firmware versions, firmwares have different numbers based on the release which is available at that time from Stelar, and right now our latest firmware version is F04. Then we have our software version, which in our case is this one, and these numbers change based on the improvements which we add, the features which we add, because Storm 6 is a software which is always evolving. We are always adding new features in it. We are improving its stability based on our customer feedback, based on their requirement. We always add features and make it more reliable and user friendly for the user. So for us, user feedback is really necessary, and based on their feedback we manage our software Storm 6. So this is one indication to make sure that software and firmware are communicating. The next part from which we can see if they are communicating is we can see it from here. Okay, let me go back. This is board status. So when we see ready, it means software and console are communicating. But if it's not ready, if this status is connecting, then it means software and console are not communicating with each other. And to establish the communication, what we have to do is to go to control panel, press restart Storm 6, and then we have to select OK. So the software will go through this stage. It's not a problem, we just have to accept or press enter again. Then the software will establish the connection. You see it's now in checking mode. So when it's in checking mode, it means the software and console are not communicating with each other. Then we and when it changes to ready, it means now the connection is there, and when connection is there, then we are allowed or we are ready to perform an experiment. But before performing an experiment, Storm 6 always checks that all the safety alarms are okay, all the connections are okay, and there is nothing which could stop us from performing experiments or which could affect the experiment's reliability. So it always checks for different signals, and whenever there is something wrong, something unusual, it tells you here. So if you see this PLC alarm present, it means something is not okay. And what is not okay, this we can see from here. So we have to come here, and it tells you right now we have these two alarms. So this alarm has some problem, and the other thing is that the water flow is also not okay. So when there are alarms, then we cannot switch on of the console. Even if I try to switch on from here, this is the cooling which is necessary for the magnet. If I try to switch on, I will see errors. So it will. After understanding the hardware of Smart Tracer and getting familiarity with the basic structure and interface of software, the next part of our training is to perform real NMR experiments. And today, for our training purposes, I have selected cheese as a sample which we will test and which we will use to perform NMRD experiments. And the reason of choosing cheese is based on the nature of our training school. So what we have to do is we have to click on new experiment in order to start an experiment. And the first part, whenever we have to perform an NMR experiment, is to make sure that we have the proper working conditions and our probe is properly tuned. And to do this, what I will do, I will create a new experiment, and I have named it as resonance tune. And the sequence which I will select for a FFC instrument is non-polarized. So this is a single block non-polarized sequence. We can also use pre-polarized, but I generally prefer to use non-polarized sequence. And the nature of the sequence which we have to use also depends on the sample. If the sample which we are using, we want to relax it at higher field or at lower field, and how much signal it is generating. So as you can see, this is the main interface of our software, and the main interface has few parts. So the first part, which it tells us about, if we see here, it tells about the workspace which we have created. And in this training, the workspace which we already created is NMR training. The sequence which we are using is NP, and this is the date at which it was created. Here it's the name of the experiment which we just gave. And then you can see these are some important parts of the interface of Storm 6. It tells us about the parameters. So this parameter part tells us about some of the important parameters related to performing experiments, like RD, radiation delay. It's measured in seconds, and this here it tells you about its minimum and maximum range. So this basically is the delay between two blocks. If the experiment is multi-block like NPS, inversion recovery, saturation recovery, or if it's a single block, then this is the delay between two scans. Then we have receiver inhibitance and acquisition delay. So these basically are the delays before the start of an acquisition, and in this we give proper time for the experiment to settle before, to avoid those transients and give time to receiver to start the acquisition. And then here it tells this acquisition, which is in microseconds. This is basically the time of the total acquisition. So this is the time in which the NMR signal will be occurred. Then the relaxation field at which we will relax our sample in a single block. This tau tells us about how much time the sample will be in high field, the relaxation field. Then we have the ramp. This basically tells us about how quickly the instrument will change from one field to another field, and this is the important feature of FFC instruments, that we can switch the field from one field value to another value. And this is acquisition. This is the field at which we will acquire NMR signal. Then we have another tab which we call pulses. So this is the 90-degree pulse which we are transmitting. This is the spectral frequency. This is also the frequency at which we tune the probe. And if in case the system is out of resonance, then we compensate it with these values. And this is what we will do first of all in our today's experiment. And then this is the part which is basically how much the transmitter voltage has to be. This is in millivolt, as you can see here. And this is important because it affects the pulse 90-degree duration. It depends on sample, the instrument, and how short and long we want to make our pulse duration. So this we can tune from here. Then we have some hardware parameters which we can see from here. So here we can set how many number of scans we want to perform. Then this is the duration in microseconds. This is how much our pulse 90 degree is. So this pulse 90 degree is basically 6.15 microseconds. Then here is our sample temperature. This is the temperature which this is the temperature in which currently the sample is, and this temperature we can increase and decrease either manually, which I have already explained, or from software, which I will explain to you now how you can manually increase it from automatically increase it from software. And this tells us about how many number of points are there when in our FID. So by default it is 1000, but we can increase and decrease it. Then this is also sweep width, which is basically related to the sampling frequency, how short, how quick or how slow we want to sample our signal. And then here are some filters. So we have some digital filters. The 5 mega is basically the open filter. Then we have some other filters which we will use during our experiments. And what I generally prefer is 1.25 mega, but we can increase and decrease the bandwidth, the band of the filter based on how much noise we want to remove, or what window we want our acquisition to be in. And then we have some important parameters related to this. Is related to the phase cycling. So let's say if we have multiple scans and we want to cycle their phases and accumulate them. So with this we can add different scans with each other in different orientations. And this information we can see from here. It tells you we can use x minus x, y minus v, and what they basically means, how they add or subtract real and imaginary parts between multiple scans. So this is useful when we perform multiple scans. In single scans it's not that much useful. Then here, this is the part where we basically set how the dimension of our blocks. So, and then these blocks can be these blocks can be linearly distributed, logarithmically distributed, or we can also write a list of the tau. So this basically is the distribution of tau. This is a single block. So in this experiment, this part is basically empty, but in other experiments which we will do later, like NPS, we will see how this part we use it and how we tune this part. Then we have some hardware parameters. If we have multiple scans and we want to accumulate them, this we can do from here. If it's 1, it means on, accumulation is enabled. If it's 0, the accumulation is disabled, it's off. Then we have these parameters for transmitter and receiver attenuation, and these also depends on the hardware which you will use and how you want to tune your experiment. So by default, what we generally do, we receive with the receiver attenuation of 0, and then we see if the received signal is saturating, then we increase it one by one till the saturation is removed. So this is how we see what value we have to use. And this is receiver attenuation. So what I generally recommend to use is 22 as transmitter attenuation. So this and this, so these two together are used to tune the pulse 90-degree durations, and by increasing and decreasing these two values, we can increase and decrease the duration of the pulses. And then we have our evaluation tab. Here we can set how we want to evaluate our signal and how many blocks we want to use to compute the T1 relaxation values, and inside each block how many points we want to use. As you can see, there are 1000 points, but it's possible instead of using 1000 points, we can use only a limited range of those values. So if by default it's 1 0, which means it will take all the points, but if we write instead of 1, if I write, let's say 10 and 300, so now it will start from 10 to 300, and these points will be now used to evaluate the T1 value. So the T1 value which we will see will be based on this starting part of the FID, so we will not take into account the whole FID, and this information is also written here, which we can see from here. And then we have our absolute values, how we want to plot the relaxation value. So by default it's absolute value, but we can change it to real value, we can change it to accumulated modulus, any kind of value which we want to which we want the software to use to compute the relaxation values. And then we have type of fittings. So by default it's mono exponential, but we can plot multi-exponential values of the sample if the sample has multi-exponential nature. So this we can select from here. And then these are some other parts of the experiment which, as we will perform experiments, we will understand. But before starting an experiment, it's important to make sure that the software and console, they are communicating, and this we can verify from here. When we see it says terminated or it says ready, if we see if the status here is connecting, it means there is no communication, and we have to establish the communication from here by clicking restart storm 6. So in this way the connection will be re-established, and this we can see also from here. So as you can see right now the firmware version is F04 on the, and this means that software and console are communicating, and the software version right now is 1.21. so this is the version which we are using now. So before starting an experiments, we have to make sure that the magnet is on, and magnet will be switched on only when the cooling is on. So we will start by switching on the cooling, and then we will switch on the magnet, and if we do not see any alarms, it means everything is okay. And if everything is not okay, then the magnet will not be switched on, and we will see some alarms here. And the next part is to set the sample temperature. As I've already explained, that the temperature of the sample can be controlled manually and also through software. So right now the temperature of the sample is 24 centigrade, but for our experiments I will set it to 25 centigrade. So I wrote 25, and then I have to press set. It will ask me that this value is okay. I will say okay, and then you will see this temperature will start increasing. So before initially it was 24 centigrade, and now this will gradually increase from 24 to 25, and when the temperature reaches 25, it will stop there, and the temperature will be maintained. So it will take some time based on how much we want the temperature to increase. So as you can see, it's increasing, so it will reach 25, and then it will stop there. Okay, so now we have everything set. We understood the experiment, the software, all its important parts, and so the first thing is to get the proper resonance conditions for our experiments. I have selected NPS, and now I will get those values. But before that, it's important to make sure that the probe is properly tuned, and to do this we just have to click on tune right here, and then we will press start. So as you can see that the probe is properly tuned, and the span is really big, so that's why the tuning we cannot see it more clearly. What I will do, I will decrease the span duration from 4 to 1, and now you can see that the span is much reduced, and we can see that the tuning is okay. So the dip is the point at which the probe is tuned, and this we can see from here. We can still further improve the tuning by manually switching the capacitors which are located below the probe, but for our testing purposes, let's say this is okay. and if we had to tune it to some other value, we just had to write that value here, and then we will see if it's properly tuned or it's not tuned. So right now it's tuned, so we do not have to do anything. I just press set frequency, and once we press set frequency, that will be updated here, but for in this case both are same, so the value remains same. And now the first thing is to do is to get resonance condition. Basically the second thing, the first thing is to tune the probe, the second thing is to get the proper resonance condition, which we will get from here. We just have to press start. So now we see that the system is not in resonance, it's out of resonance, and to get it in resonance, what we can start with F1. We can see these values are changing, and if we will press it 2-3 times, we will get to the resonance condition much quicker. Okay, we can also get the resonance conditions manually if we can see, if we can understand where it's going. You see now I enter 12 and the system is in resonance. This value generally I prefer to use 200, so I will use 200, but this will just increase the signal level. And it's important when we get the PW 90 degree of our sample. So now we have performed an experiment in which we got proper resonance condition, and we can see there is offset of 12.1 kilohertz and the receiver phase has to be 53 degree. And now what I have to do, I just have to press set resonance. So after getting the resonance condition, the next step is now to get the proper pulse duration, which we already have, but what I will do, I will re-verify it if the pulse duration which we are using now, if it's correct or we have to change it. So what I will do, I will start another experiment, and this experiment is called angle. So you see the angle FF is the sequence which is used for fixed field systems like 3T system which we have. For field cycling systems like Smart Racer and Spin Master, we have another sequence which we call angle FFC. So we will use this sequence. I will name it power of pulse. This is just I am giving simple names based on the type of experiments which we are doing, but this the user can give them any name which they prefer. So we perform this experiment where we got the resonance conditions. Now what I will do, I will just press set get resonance, and you see these values changes. So this is how from this experiment we get resonance condition, and we can use them in another experiment. And now when we perform an angle experiment, it's important to make sure that the parameters are consistent. So you see right here we used 14 and 5, so we have to use again 14 and 5. And in angle, because this is a cheese, so for cheese the best thing is to give it some time at relaxation value due to its nature and I value of T1. So I gave it this 0.5 as tau. We are relaxing at 8 megahertz, and other parameters are mostly okay, and these should be the parameters which we have already used when performing or getting the resonance condition. So we use 10 and 5. We will use again 10 and 5 here, but I think instead of 10 and 5, let's go with some filtering. I select 1.25, so the filtering basically does not affect the resonance condition, but I just tried it anyway just to make sure that the resonance condition still remains same if we change anything. And then these values, we have to make sure that these values are okay. So this is something which I will change. So okay, so they did not change the resonance condition, so this is good because we have to verify. It's important to make sure that the parameters we use to get resonance condition should remain consistent in other experiments. And then this is NDIM. As I explained to you, if the sequence or experiment is multi-exponential, then we will see this part visible, and then here we can write how many values we want, the starting value, the ending value, and this is in microseconds. This distribution can be linear as it's here for angle sequence. It can also be log, or it's also possible to write our own list of values, and these values just have to separate it by commas, and how many values we write, the software will take it as number of blocks. So that's how we can write our own values. So we have everything okay, and what we can do is now just press start and see how the experiment goes. So if you see this alarm, so it's this pop-up, so it's not a problem. You just have to press OK and it will. And this is because the Storm 6 is a web-based software. So if we perform an experiment in one tab and we go to the other tab, so the software is still in the previous tab. So that's why it asks you that the software is busy in another experiment. You want to start a new experiment, and we say OK, and then it will kind of disconnect from that experiment, and then a new experiment will begin, as we can see here. And now we wait for the angle experiment to finish, and with this experiment we will get the pulse duration of our sample. So right now the signal is at pulse duration of 6.15 microseconds, but here now we will see if this value is okay, if it's not okay, what is the new value. So when we perform so we will allow the experiment to finish, then I will explain to you some other parts. But here you see there are some other options related to data management. So with this tab, download data, we can download the data from each zone. We can also download complete experiments. We can delete zones and delete all zones. So what are zones? This I will explain to you in a later part of the experiment. Okay, so we have our angle experiment. To be sure, we have to see, okay, so as you can see that we have this 180-degree crossing, so the real part starts from positive and then it goes to negative. So we can say the angle experiment is okay, and we are quite happy with what we got. The next step is to know what is its value which the experiment has calculated, and this we can calculate from here. We just have to press set PW90. So the value it gave us is 7.18 microseconds, and this value we can increase and decrease by increasing this value. If we increase this value, the 90-degree duration will decrease, and if we decrease this value, the 90-degree duration will increase, because this will decrease the attenuation of transmitter, so it means more signal power, and increasing this will increase the signal power, so it means the 90-degree pulse duration will decrease. So but let's keep things simple. So we have a new 90-degree duration. You see this is the old duration, but if I will refresh this page, it changes, so it automatically updates to the new value which we have calculated. So we have performed the basic steps. We have tuned the probe, we have calculated the resonance conditions, we have also calculated the pulse duration, and the next step is to get the relaxation values of our sample. And to do this, I will start with NPS. So this is a non-polarized multi-block experiment, and I will just name it cheese sample, and this sample has a duration of around 24 to 28 months old. so I gave it just name to understand which sample we are using now. So we have our experiment which we have already performed, and now the next thing is to get to perform the experiment and get the relaxation values from this sample. So but before starting the experiment, it's important to set the experiment in proper conditions, which is to make sure that the resonance values are correct, which we will verify from here. So I pressed get resonance, and you see these values are updated. This is okay, but this value updated -12 and 53, so this is okay. These values are okay, and so this radiation delay basically depends on what is the T1 value of the sample, and the rule of thumb is it should be at least 3 to 4 times bigger than the T1 value of the sample which we will use. So here for this I am writing 0.5 as the T1 value, so that's why I changed it to 1.5, but this will increase and decrease based on what is the T1 value of the sample which you want to measure or which you are using to perform experiments. And then other things are okay. This we again have to make consistent, so 22 and 0, and these are again okay. So as a first step we will do mono exponential fitting. So here we can see it's mono exponential, it's absolute value. And what I will do, so I will compute, let's say 32, and I made it 6, and this is the distribution. So normally 16 is okay for mono exponential samples, but since cheese has this multi-exponential behavior, so that's why I increased the number of blocks so that we can get shorter and longer T1 values if there are. So when everything is okay, we just have to press start, and we will see the experiment starts. So you see the experiment started. It will go block by block based, and the duration between each block is 1.5 seconds. This is the time which we are providing to the sample and the instrument to relax, and then the duration of each block is determined from here, which is logarithmically distributed. So the maximum is 6 multiplied by T1 max, which is here. So 6 multiplied by T1 max is basically 3 seconds, and then the minimum is 0.01 multiplied by T1 max. So that's how the blocks will be distributed logarithmically. And inside, so when the experiment finishes, we can see it finishes from here. It said experiment successful. The thing is to see the fitting chart. So like the experiment we performed, what are the values of relaxation? So for this we just have to press evaluate, and then we will see this mono exponential fitting. So you see the T1 value is around 111 milliseconds, and then this is the percentage error is really low. So these are the mono exponential values, and this we can see from here. So we just have only 1 point here. But let's say if it's the sample is not mono exponential but it's multi exponential, how we can compute the multi exponential components? It's really simple. We just have to select by. It will show us the formula which it will use to calculate the bi-exponential components. The expert users can verify it from here if they think the formula is okay, and if they want to tune it, they can tune it from here. So with multi-exponential components, this is the case mostly, that the formula which we use needs a kind of tuning because to get the proper components. So because each component have different weightage, different T1, different relaxation times, so it's not always possible that the default formula will give you the correct results. So this is recommended to users, to expert users, to verify the results based which they see and the nature of the sample, because they already have some idea about how the sample should behave, and then they can tune it from here. So the experiment is already performed, so we do not have to perform it again. We just have to press evaluate. It will take the acquired data to the process, and then it will give us the multi-exponential values, which we will see now. So you see now we have T11, T12. So at this field value 8 megahertz, so we have one component which is more evident, and then we have another component which is not that evident, and here it also tells us about its weightage. So one component is around 87%, the other component is 13%. So this because at higher field cheese mostly behave as mono exponential. At lower field, this is the area where we see the true multi-exponential behavior of cheese sample. And then in NMRD chart now we have two components which we can see from here. So these are their relaxation values, and if I refresh this page, you will see that these are the values. So these are R1 and T1 values. So that's how we can perform multi-exponential and mono-exponential components. So I performed at 8 megahertz. Now I can perform the again same experiment at 5 megahertz. So this time what I will do, I will start with new zone. So this what this will do. So with Storm 6 you can perform many experiments, and you can easily manage your data in workspaces and also within experiments by performing experiments in multi-zone. So in the first zone we perform the experiment at 8 megahertz. In this zone I am performing the experiment at 5 megahertz. So it's 5 megahertz, and now you will see, so because now this is just one zone, but once this experiment finishes, there another option will appear here which will be 2. So in this way we can increase the number of zones in how based on how many new zones which we created and where we perform experiments, and then these points will be added together. So you see now we have only one point at 8 mega, but once this is finished, okay, so the experiment is finished, you see now we have two zones, but this zone is not evaluated. So I have to press evaluate. So these are the previous values, and then this will be updated with new values. Okay, so the evaluation is done, and you see now we have two values, and this value is almost negligible. You see the value is really small, and these are again the contribution. So the second, because 5 mega is still at higher field, so one component is more it has more weightage as compared to the other component. So with Storm 6, as I showed you, without using our instruments, the field cycling instruments, we can get relaxation values for mono exponential, for multi exponential values at any field value which we want. We just have to write the field value, press start, and the software will automatically calculate the value. The hardware will switch it from one field value to another field value, and in this way we can get the relaxation values at any field value. And that's how time division instrument works. But the problem with them that they are good at measuring or evaluating the T1 values at one fixed value, but with field cycling instruments like Smart Tracer and Spin Master, we can compute these values in a range of values. And now I will explain to you how we can do that in using an NMRD profile. So this was single exponential. Now the next part which we will do is I will explain to you how you can do all this automatically using NMRD profile. As we can see here, the NMR profile is about to end, and cheese has a really heterogeneous nature. So due to this heterogeneous nature, it has water, fat, protein, and based on the age of the cheese is the relaxation values, this curve, the component, they gave different kind of profile values. So that's why we can see here that at higher field both components are more or less in the same range, but as we go down the component values increases, and now with these values it's up to the experts and analysts to see if these values what they are getting, are they okay, or if they need they can also tune these values, this play with this model to get the behavior which is most approximated and expected. But from software, what we can do is we can perform experiments from really high field to really low field, and in different zones, and at different relaxation values, and at each relaxation values field value, we can get the relaxation values related to that. So I will now conclude this training here, and at the last part of the training I will share some NMR profiles which I have performed here, and those NMR profiles are for different cheeses, and they were, so the nature of the cheese is same, but they all have different ages, and from this we can see that as the age of the cheese changes, its relaxation value also changes, and using Smart Tracer or Spin Master with our FFC technology, we can get a really good idea about the nature and behavior of the samples. So I hope this training was helpful in some way to all of you, and now you will be much more familiar with how to perform experiments, how to set parameters using our technology, our software, our hardware, and a basic understanding of the FFC technology in general.